right, so let's continue our discussion related to bipolar junction transistor. So all of you are familiar. We'll discuss the NPN transistor. NPN transistor. So we know the symbol of NPN transistor here. This is our base, this is our emitter, and this is a collector. We also, usually we know this also, the simple cross-section of a transistor. So we have emitter here, base here, collector here. So this is our N, this is our P, and this is N here. Emitter, base, and collector, right? All right, so this is our transistor. And so what we need to do is, we said we need to understand this from a circuits perspective, okay? You can understand something from different perspectives. So from a circuit perspective, how does a circuit designer look upon the bipolar transistor? So in that context, we were saying that if I look at it, I have three currents, obviously. I have the current IC, and I have current IE here, and I have current IB here. These are the here. And we were drawing the output characteristics. Output characteristics where we are talking about IC. Normally, the output is taken at the collector. So we are talking about, these are the terminals here. So we were talking about this characteristics here. IC and VCE. And we have a characteristics of this kind, right? And we said we have all these different characteristics that are there, and these are for different values of IB. This could be IB1, IB2, IB3, and IB4. All right, so these are what we call as the output characteristics. Output characteristics. Why? Because it refers to the collector current and refers to the output voltage here, collector emitter. Let's say emitter is the common terminal, and therefore this refers to the collector current versus the collector voltage here. All right, so that's why we call it the output characteristics of the transistor here. And in that we saw that there are three distinct regions, at least from here, a distinct region we can find. That we have a region here which we call it as the active region here. Active region here, and we have a region, all this region that we call as saturation region here. All right, so two regions that are obvious from here. And we said also that this region that you see here, the active region, the current is changing very slowly with the voltage here, almost like a flat characteristics here. And first order, we can think of this particular current as like it is a current. We can think of between collector and emitter, first order between collector and emitter. If this is collector and emitter, we can think as if between collector and emitter we have a current source, and the current source, because it's not varying with function as a function of voltage. So a current which doesn't vary as a function of voltage, we model it as a current source. And the value of the current source depends on the value of IB1, IB2, IB3 here. So we write it as a dependent, and we call it the beta IB. Okay, so we said this is the transistor in active mode is acting like a current controlled current source, right? Current controlled current source, CCCS. All right, so if you want to make it more accurate, then what you need to do is you need to take into account the fact that there is a slope here. Okay, there is a slope here, and the current is not simply beta times IB, but what we can write is if we were to exaggerate this region here. All right, so let's say, let me go here and take a transistor and take one of these characteristics here, and let me exaggerate a little bit here. Exaggerate here. IC versus VCE. If I were to exaggerate here, right? Exaggerate the slope here, right? Slope here. So there is a slope in active region. And if I were to exaggerate, it would look like this. But if I take here, it's almost like a linear variation here. If I take here and extrapolate it here, it would intersect at a particular place. Note that this is the collector emitter voltage here. We call this voltage as the early voltage here. Early voltage here. So the early voltage characterizes the slope of this particular line. And IC, we can now write not just beta times IB. Beta times IB is, when you don't take into account early effect. So it's beta times IB multiplied by 1 plus about VC. We model it like this, VC by VA. So this is a more accurate description of how current varies in the active mode. This we are talking about the active mode here. So current has a dependence on IB and current has a dependence on VA here. Now value of VA of course varies from transistor to transistor. For example, VA could be, let's say VA could be 100 volts. So you can check that as you vary from, let's say if VC is at this point, let's say VC is 1 volt, and then you go to, let's say VC equal to 5 volt. If you go from 1 volt to 5 volt, what would be the change, corresponding change in IC? Delta IC would be beta IB delta VCE by VA. And percentage change in IC, because note that VA is large, so delta IC by IC percentage approximately equal to this we can take it as basically equal to IC, so approximately equal to delta VCE by VA. So this is equal to VC, we are talking about 5 minus 1, 4 divided by 100. So we're talking about 4% variation in current here, right? That's why we say it's relatively very flat. Right? Typical value may be 100 volts here, and therefore you find current is only changing when you go from 1 volt to 5 volt, current is only changing by 4% here. All right, so that's the thing to keep in mind here. Okay. So normally beta IB, but if you want to be more accurate, then we'll multiply it by 1 plus VCE by VA. We'll multiply it by that particular factor here to be more accurate here. So that's how the transistor appears in the active mode. Okay. Now in the input side here, suppose I look at the input side here. As you know, what we are doing is we are taking, let's say, emitter as the common terminal here. Emitter as a common terminal here. This we are talking about this as an output terminal here. And this we are talking about as the input terminal here. Many times signals are fed into the base and output is taken at the collector, right? So this is the normal, when emitter is ground, this is the normal, what we call as the common emitter configuration. Common emitter configuration, right? So if I look at the common emitter configuration, so output side we've already seen. Output side, once the transistor is in the active mode, it acts like a current source that you see here. Current dependent current source here. This we've already seen. From the input side, how does it act like? Well, let's draw from the input side. Input side, what do we see from the input side? You know, input side, the current is base. So input characteristics, we plot base current. We plot base current versus base voltage, and emitter is the common terminal here, IB, VBE, right? And in the active mode that you see here, what we do is, you already know this, what we do is this junction we are forward biased and this junction is reverse biased. Okay, so the emitter based junction is forward biased and collector based junction is reverse biased. So we are applying a positive voltage to the base here, note that is forward biasing the junction, and the current that you see here, the base current that enters here, because this junction is reverse biased, the base current primarily comes about because of injection of carriers like this here. This is the forward bias junction. So the holes that you see here, they get injected into the emitter here, forward bias junction. The collector current, we will come to that. The collector current, on the other hand, so IB is primarily when you apply base emitter voltage. So what you see here is a PN junction. So IB and VBE is nothing but a diode characteristics. You see a PN junction diode. So it's like a forward bias characteristics here. So IB, if you would like, IB would be equal to some, some saturation current. Let's say IBS, e to the power VBE by VT minus 1, right? So that's how the input characteristics look like. Input characteristics. Input characteristics, okay? All right, so the transistor looks like a diode, and from the output side it looks like this thing here. So if you put both of them together, the input side is like a diode, output side is like a current source. So let's put both of them together. So we are talking about this transistor in the, let's say, common emitter mode. Let's put this as ground and let's put this here. So base, emitter, it need not be ground, let's put it, except that we are talking about as a terminal here. So if I want to look upon, as I said, from a circuit designer's perspective, what are we going to see? Let's draw emitter as a common terminal. Emitter is a common terminal here. Let's draw a base here, and let's draw a collector here. Collector here and base here, right? Between base and emitter, what did we see? What does it look like? Looks like a diode. Looks like a diode characteristics, right? So what should I put between base and, between here and here, I should put a diode here. Between base and emitter is a diode, and the current flowing is IB. Between collector and emitter, what did we say? Note this current source, current control current source. So we should put here, if we want to make the complete model of the transistor, we should put it here, beta IB, and to be more accurate, we should put here 1 plus VCE by VA. This is what we are talking about in the forward active mode. Active mode. Remember, active mode. That's what we say. This is in the active mode. And sometimes we also add the word forward active mode. Forward active mode. All right. Now if you look at it, let's we can draw here. When I look at my transistor, let's draw here is N and P and N here, right? Emitter, base, collector. Emitter, base, and collector here. Let's suppose we draw here VBE and we draw here VBC, right? There are if we take emitter as the there are two independent. There are 3 voltages here, right? There are 3 voltages: VB, VE, and VC. 3 voltages here, which we can describe in terms of a base emitter voltage and a base collector voltage. Okay, this thing here. So base emitter voltage describes the PN junction diode here, and base collector junction base collector describes the PN junction diode here. So in this case, when VBE and VBC are both positive, note that both the junctions are forward. Both junctions are forward bias, right? In this case, note that what we forward bias, the first letter denotes the base emitter junction, and the second letter denotes the base collector junction. Okay, forward. In this case, what do we have? Forward reverse. Under this thing, in this case, reverse, and in this case, reverse forward, right? These are the characteristics of the junctions in these four quadrants. Here is where we call the transistor as saturation. Both the junctions are forward bias. We call this saturation. Here is what we call, this is the what we are discussing. Base emitter is forward bias, collector base junction reverse bias. We call it the active region here. And we call this, you will see, we call this forward active, to be more precise, forward active here. Called it the forward active, saturation. Now this, the other one is exactly opposite to this. In this case, the base emitter junction is reverse bias and collector base junction is forward bias. So this is also active, but this we call as the reverse active. And when both the junctions are reverse biased, reverse bias junctions don't carry much current. So this is what we call as the cutoff state. Right? So these are the four broad regions in which I can operate the transistor. What I've been talking about right now is the forward active region here, forward active mode, because that's where we make the transistor, we make amplifiers, which will become clear in a minute towards the end as to why we use the forward active mode to make amplifiers rather than cutoff. Obviously you will not make cutoff, means device is off, it's not conducting current, so it's not of interest. So you have the possibility of forward active and reverse active, and then you have the properties of saturation. Now between forward active and reverse active and saturation, we'll come to that, but this is the model that we have for a transistor in forward active mode. We just saw in the forward active mode, this acts like a diode and this is like beta IB ICs. Now for analyzing the circuit, for circuit analysis, often what we do is we use a a simplified version of this. So we have base, and to the diode what will we do? We talk about DC for DC circuit analysis. Okay, DC circuit analysis. What am I going to do to the diode? Assuming we have had discussions that the voltage in series with the diode must be pretty large as compared to 0.7, right? Then only you can replace it, otherwise you have a problem. So we replace it by a 0.7 volt here. The current here is IB. And as I said, for DC circuit analysis, we replace this by here. And we ignore this factor here, 1 plus VC by VA that you see here, because it's a small factor. We simply write beta times IB. This becomes a model: base, collector, and emitter. This becomes a model, simple model. So if you have to do a DC analysis of a circuit containing a transistor, what do you have to do? First, figure out, is my device in forward active? Is it in reverse active? Is it in saturation, or is it in cutoff? You have to identify which mode is it working in. Once, if you know that this is in forward active, you can analyze using this particular model, and it will give you simple result. There would be some error. We are neglecting a few things. We are assuming 0.7. It's not exactly 0.7. We know that. We are neglecting the early effect here. It's not just beta IB, it's beta IB multiplied by 1 plus VC by VA. We are neglecting a few things, but it gives us a reasonable answer. Okay, gives us a reasonable answer of the transistor circuit here. Okay, so this is in forward active. Now, sometimes what we do is, just to be clear, this beta that you see here, we write it as beta F, because note that it refers to forward active. So beta F. Now, if I were to draw, see, this is forward active. If I were to draw the circuit for reverse active, what will I get? This is for base emitter junction forward bias and collector base junction reverse bias. If I were to draw for reverse active, what circuit will I get? Just by analogy. We've already done this, so by analogy, what will we get? So if I were to draw so there is a base here. What should I take the common terminal now? Are you seeing the role is interchanged? The role of collector and emitter is interchanged in reverse active. Which junction is forward bias? Which junction is forward bias in reverse active? Base collector junction. So what I should do is, I should write here collector, and between collector I have a forward bias diode, right? And I should write here emitter. The role is interchanged, and I should put here a current source also, except that I should put here now beta R reverse IB. I should put here beta R IB. So this is emitter, right? That's how I should draw a reverse active. Yeah. This is reverse active, RA. Reverse active. And this is forward active. Forward active. Both are very similar, except that note that collector and emitter have been interchanged, right? Now, if you focus on this one, right? Focus on the transistor. Emitter is what? N. Base is what? P, and collector is N, right? Both emitter and collector are N types, and base is P type. So it appears that I can interchange them, right? But the bipolar transistor is made in a asymmetrical fashion. This is not just N, this is N plus, heavily doped. And actually N, the collector, is actually lightly doped. So it's actually asymmetrical. It's not that the emitter and collector are exactly the same. They're not. They're asymmetrical. And as a result of which, what we find is that beta F is much, much larger than beta R. The gain, the current gain that we are talking about, the forward current gain, beta F is much, much larger than beta R. Beta R may be, for example, 1 or 2. As an example, this could be, say, 1. This could be 1, and beta F, we are talking about 100. Right? So in one case we are talking about reverse gain as only 1, and in one case you're talking about gain of 100. So that's why we don't bother about reverse active. The transistor has not been designed to work in the reverse active mode. It has been designed with emitter heavily doped, and so that the emitter based junction should be forward bias and collector based junction should be reverse bias. It has been designed with that purpose in mind, and that's why we do not use this. This is not used. There would hardly be any circuit that you would find people using transistor in a reverse active mode. They don't use it. So you end up using the forward active mode. So reverse active is not of interest. Cutoff state is straightforward. Both junctions reverse bias, so it's like the transistor acts like an open circuit. The saturation is more interesting. Okay, so we can look at saturation. So saturation, look at saturation. So let's put here. This is like N plus, this is like P, and this is like N. Here. Base, emitter, and collector. Right? So saturation means what? Saturation implies both junctions are forward bias. That's the first thing about saturation. So both junctions are forward bias. You know that VBE, if it is forward bias, would be around 0.7 volt. It's a forward bias junction, right? Base collector junction is also forward bias. So VBC should also be, what should be VBC? Forward bias junction. Also 0.7. Except that, note that this junction is N plus and this junction is N minus. Okay, so what it does is, this is 0.7 volt, 0.7 volt may be needed to get a 1 milliampere current. Okay, while here you may find that you need only 0.5 volt to get 1 milliampere current. The nature of the junction is different. It's a lightly doped junction. All right. So when we say, typically when we take VB equal to 0.7 for a emitter based junction, and we take slightly lower VBC equal to 0.5 for a collector based junction. Right? So both junctions are forward bias. And when both junctions are forward bias, we know that as you are changing the current, if I go from 1 milliamperes to, let's say, 5 milliamperes, what will happen to VB? Not change much, right? We said. Remember diode voltages? Diode voltage was what? Diode voltage, V diode was KT by Q, ln 1 plus ID by IS, right? So the diode voltage doesn't change much if you change ID. So if I have a transistor, it's carrying 1 milliampere current, maybe 0.7. If you 5 milliampere current, a little bit larger than 0.7. Similarly, this voltage also doesn't change much because they're forward bias. So forward bias diode voltages do not change. So if I take these numbers, note that VBE minus VBC will be what? What is this? VBE minus VBC. But what is this? When I write VBE, what do I mean by that? VB minus VE, right? Right. And this we write as VB minus VC. So this is equal to VCE. And what are we saying? VC is about 0.2 volt. So in saturation, what is the characteristics that we get? VC is some small value. See, it's not so important that this is 0.2. It's some small value which is relatively constant. This could be 0.1 also. This could be 0.15. This could be 0.25. That is not so important, except that it's a quantity which is almost fixed, doesn't change much. So when I'm thinking of my transistor in saturation region, note that, let me draw this base, let me draw this emitter, and let me draw this collector and base. What should I put between base and emitter? Between base and emitter, what should I put? At least same diode is still there, right? Same diode. I'll put here. Between collector and emitter, what should I put? What are you finding between collector and emitter? A voltage source of a value about 0.2. So in saturation region, you think of transistor like this, roughly. You think of it like this, 0.2. Some people call this, instead of VCE, they say VCE saturation. This is in VCE sat is about 0.2. Or if you would like, you can write here, you can, if you want to be accurate, you want write here VCE sat. Note that this is IB and this is IC. Right, that's the nature of saturation region. Okay, all right, so let's compare the two. It's important to look at both the transistors. Here is our transistor. We are talking about NPN transistor. Active region. Now active, whenever I say active, please understand that we mean forward active mode. Okay, we will not say that, but it's meant that forward active mode. Our transistor looks like, you should be able to draw this very quickly, right? Beta IB here, depending on how accurate you want, emitter and base here, forward active. Note that this is IB and this is IC. One of the thing is, in forward active you see IC is equal to beta times IB. This relationship holds. IC is equal to beta IB, and the other one is base emitter voltage is roughly 0.7, right? So we use these things to calculate it. VB is equal to 0.7 volt. In saturation mode, compare the two. We again put here we draw here emitter, again same diode, and but we put a voltage source here, VCE sat, right? So again, what when we analyze circuits, collector, analyze circuits, we will assume VBE 0.7. Sometimes people take a little higher also, VBE, and we'll assume that VCE is 0.2. Note that IC is not beta IB anymore. IC is not beta IB. In fact, from this characteristics that we drew, remember output characteristics that we drew, the transistor acts like this, IC versus VCE. This is active, this for some IB. So in this active mode, IC is equal to beta IB. In saturation, what do you think is, this is saturation. What do you think is IC by IB? Is it equal to beta, greater than beta, or less than beta? This is saturation, this region. Here is IC is equal to beta IB. So here, obviously less. So IC must be less than beta. Here is where saturation is. So one of the characteristics of saturation is what? That IC by IB is less than beta. Or another way that people write it is IC by beta IB is less than 1. Important relationship. This is one of the characteristics of saturation, that IC by beta IB is less than 1. The other one is we take VC equal to 0.2 and VB approximately equal to 0.7. So now you know, these are all DC models, by the way. We are talking about DC model. When we are not talking about transient, or when the frequencies are high, then all the capacitances and everything else will come into picture. We are talking about DC model here. Okay, so these are the two models. All right, so let's apply these models then. Let's look at the application here. Okay, let's see. Let's give you a circuit. Let's take a circuit. Let's put it to ground. Simple circuit we take. VCC equal to 5 volt. Let's put here 1K. And let's put here 430. Let's put here some 430K RB, right? And we want to analyze this particular circuit. Analyze this particular circuit to find out what? We want to find out what is IB, we want to find out what is IC, and we want to find out what is VCE. All these things we want to find out. And when somebody gives you a circuit like this, well, you should ask what is beta. So let's say beta is 100. All right. So how do we analyze this? Note that when you are given a circuit like this, the first issue is, remember what we said, the analysis requires what? How do you do analysis? Analysis is based on KVL, KCL, and what else? Models. Now in this case, we recognize everything, so we need a model of BJT. We need the model of BJT. But BJT, unlike a transistor, BJT is complex. BJT is complex. Remember, we said BJT could be depending on this VBC, VBE and VBC. What is this region called? For this top region? Saturation. This one? Reverse active. This one? Cutoff. This one? Forward active. So now the issue is, different regions will have different model. So now the issue is, where do you think is your transistor working? Where do you think is your transistor working? Rule out. Is it in cutoff? Can it be in cutoff? Look at this. This is now 5 volt here, right? 5 volt here is connected through RB to the diode here. Between here and here, what do you see? Between base and emitter, this emitter is ground and base is here. Between base and emitter, when you look at a transistor, what do you see between base and emitter? Remember, that's why we were talking about model. Between base and emitter, what do I have? A diode, right? So now 5 volt here and 430K and base emitter. Do you think base emitter junction can be reverse bias? Can it be reverse bias? You have 5 volt connected through a resistor to a diode. The 5 volt will obviously bias it. So what I know is, by looking at this, that my collector, what I know is that my VBE will be 0.7, or base emitter junction is forward bias. Base emitter junction forward bias. The moment you have base emitter junction forward bias, it immediately rules out reverse active and cutoff. These are no longer the options. You have the possibilities are only forward active and saturation. Forward active and saturation. Okay, we don't know. Is base collector junction forward bias? Usually it's not obvious. It's not obvious, okay? It's not obvious. It can be, it could be base collector junction could be forward bias, it may not be forward bias, okay? So deciding between forward active and saturation is not straightforward. So the way to do that is, what you do is you assume Assume forward active. Assume forward active. Start with the assumption. Assume forward active. Right? So suppose I assume forward active, then am I in a position to calculate all these values? IB, IC, VCE. Am I in a position to do that? Can you all do that? Assume forward active and solve this particular circuit. This problem, you please do it on a separate sheet of paper, write down your name and roll numbers. We'll use it as an attendance also. Okay, we'll get some marks for that also. So just do it on a separate piece of paper. Just take out one sheet and write your name and roll number and then do it on this. Note that what I want you to do is, with this circuit, take this transistor, when you take this transistor out and substitute the model. And which model? Substitute the model, right? Which model? This model here. Right? Substitute this model here. This is what a transistor, you're assuming it is in forward active mode. Substitute this particular model in the circuit and then solve the circuit. So take the transistor out, substitute the model, solve the circuit, and get the values of IB, IC, and VCE. Let's write IB is
10 microamperes.
10 microamperes,
IC 1 milliampere.
1 milliampere,
And VC 4 volts.
4 volt. Is this the result every others are getting? So let's quickly, basically the idea is straightforward, as we said here. So we said take the transistor out, and substitute the here. So basically this is my transistor, emitter, ground, base we said is here, diode, and collector we said was simply, we'll use a simple model beta IB, right? So this is going to connect here, this is equal to VCC, and this is my base, so I'm going to connect it here, RB, which was 430K, and we connect it to also VCC, or we can connect it up, doesn't matter. We can connect it up here, we can connect it up here, 1K, right? So we substituted the model. This is our transistor model here, right? So beta IB, so we substituted the model, and then we know that if we look at this one here, VCC was 5 volt, so we write a KVL here, 5 equal to, the current here is IB, 5 is equal to IB into 430K plus the diode drop, which is 0.7, so this gives us IB equal to 4.3 by 430K, so which gives us 10 microamperes. Once we get that, then we use this relationship. So this gives us beta was 100. Beta was 100, so 100 into 10 microamperes. So that gives us 1 milliampere here. So the current flowing is 1 milliampere here. This is our collector terminal. So the collector voltage VC then equal to VCC minus IC times 10 to the power 3. So this is equal to 5 minus 1 equal to 4 volt, right? So we get IB equal to 10 microamperes, IC equal to 1 milliamperes, this equal to 4 volt. Now note that we did this analysis with what assumption? We assumed it to be forward active mode. Now how do we check whether it is in forward active mode? What is it could be either, transistor could have been either in forward active or it could have been in saturation. How do I distinguish between these two? By checking collector emitter voltage. If it were in saturation, collector emitter voltage in saturation is VCE around 0.2 or so. It's not. It's much larger than 0.2. In fact, note that it is 4 volt. Remember what is saturation characteristics? Your transistor looks like this. Transistor looks like this, right? ICVC. I mean, this is saturation. Saturation region is a very small region, 0.2, 0.3 volt here. All this region is forward active. And we have obtained 4 volt. 4 volt is much higher than this 0.2 here. So transistor is in forward active mode. So this is there. So our assumption was correct. We assumed forward active. We did the analysis and we calculate VCE. We find VCE equal to 4 volt. And so our assumption is correct. And therefore our analysis is complete. We have found out IC, VC, IB, everything. But suppose I change the same problem. I do the same problem, exactly same here. Okay. Same, looks the same, 430K. 430k, right? 5 volt, okay, 5k. What happens now? Assume forward active, right? So if you assume forward active, yes, if you assume forward active, again you will get as usual IB equal to 10 microamperes. So you are assuming. Assume forward active. Beta is again 100. Assume IB equal to 5. We are assuming forward active, so we can write IC is equal to beta IB. We'll get 1 milliamperes. Collector voltage, what will we get? VC would be 5 minus 1 milliampere into 5k. That's equal to 0. What does it imply? VC is 0. Right? Collector voltage comes out to be 0. It means it's no longer in forward active. So what we say is assumption wrong. Assumption wrong. We assume something, assumption is wrong. But what are the choices that we have? It's either forward active or saturation. So it means now transistor, it implies transistor is in saturation. Now if it is in saturation region, what should I do? We substitute the model of saturation region. Okay, so do that. Substitute the model of saturation region. Then what will we get? Note that we'll get a diode, same diode here. Emitter is here. But model in saturation region, we put about 0.2. 0.2, and this is a resistor, 5K, and we put here 5 volt. And this is the base here, and base we put here a resistor 430k. Base, this is my collector. So base current is still same, 10 microamperes. Collector current now I can no longer write. Note that I can no longer write IC is equal to beta IB. Collector current according to the figure here, 5 minus 0.2. Note that we do a KVL here. 5 minus 0.2 divided by 5k. So we get 4.8 divided by 5k. Okay, so that's how you find that IC is equal to, yeah, so it's close to that. Okay, the problem would have become more interesting if, let's say, instead of 5k, suppose I put 10k. Suppose I change this and it became 10k. Then this term would have become, this term would have become 1 milliamperes into 10 minus 5. Obviously ridiculous, minus 5. Then if we had done this, this term would have become 4.8. It would have gone to 4.8 divided by 10k. It would have become 0.48 milliamperes. All right, it would have become 0.48 milliamperes here. So IC, note that IC is less than beta IB. IC is less than beta IB. IC is less than beta IB. So when you make these circuits and you are trying to bias it in forward active mode, there's always a danger. There's always a danger that the transistor may go into saturation region if you're not careful. If you're not careful. For example, in this case, maybe we used a very large value of resistor here, collector, right? Very large value. So note that how is the transistor going into saturation? We had a circuit like this. We had a circuit like this, RB, VCC, we had put 1K and we had put 430K. And the transistor was working fine in active mode. Then we said, well, let me take RC and increase it to 10K. And what does it do? It causes transistor to go in saturation region. RC, this RC here. This resistor. It's obvious why it is going in saturation region, right? Because as you increase the value of RC, what happens to the collector voltage? Collector voltage drops. Collector voltage drops. And as it drops, we know that VCE may become small. VCE may become 0.2. Right? So as you increase RC, RC causes VCE to decrease. This causes VC, increase in RC causes VC to decrease, and eventually you may go into saturation region. So that's something that can always occur. But if RC is not enough, then it would be in forward active. That's one way. The other one is, suppose instead of RB equal to 430K, right, RB. What if I increase RB? What do you think will happen if I decrease RB? If I decrease RB, what is the effect of decreasing RB? What is the effect of decreasing RB? Everybody sees IB increases. IB increases. What is IB? IB is VCC minus 0.7 by RB. Correct? So as I decrease the value of RB, IB increases. Everybody sees IC increases. It is in forward active mode. IC is beta IB. If IC increases, then does everybody see that VCE decreases? VC, this voltage will decrease. And then what does it do? VCE decreases, and eventually if you make it too small, what will happen? Transistor in saturation region. Transistor will again go in saturation region. So what are you getting? That if the collector resistance is very large, right, or large collector resistance will force transistor into saturation. Small base resistance may also force into saturation region. So a circuit like this that you see, a circuit like this may work in forward active. But if the values of RC and RB have not been chosen properly, it may go into saturation also. All right, it can happen both. Forward active or saturation, both it can happen. Okay, so that's something. And we know now how to check. How to check. So the general method of analysis is what? Many times you don't know. So general method is assume. Assume transistor to be in forward active. Assume it to be this. Once you assume, you know VBE is 0.7 volt, and you know IC is equal to beta IB. You can use this. Do the analysis. Do the analysis. Find VCE. Find VCE. Is VCE larger than, it should be considerably larger than 0.2 volt, is larger than 2 volt. If it is, everything is fine. But if you find VCE is 0.1, 0 or negative, then it is no longer in forward active. Then you, what if is VCE? this thing? Yes, your analysis is complete. If we are writing an algorithm, yes, analysis complete. No, well, go back, assume no, transistor, no, then transistor is in saturation. Transistor is in saturation region. Now what do you assume? Well, same VB 0.7, but VCE equal to 0.2. And now you calculate IC, IB, everything. And note IC, note IC by IB into beta would be less than 1. Note that when you do in saturation, you will always find that this is less than 1. Okay, that's a general method of analysis of DC analysis of any of those circuits. Start with that assumption, forward active, and do the analysis and check. In the end, check. If everything is checked and the answer turns out to be yes, then everything is okay. Other than that, then you have to redo it. You have to redo the analysis. Okay. So would you all be in a position to solve this circuit then? This transistor Q1, this is Q2. Right? And what I want is ICQ2 to be around 2 milliamperes. Find RB. ICQ to be around 2 milliamperes. Find RB. Note the first thing that you can do is very quickly, if it is 2 milliamperes, what is the value of this voltage? ICQ is 2 milliamperes. Okay, let's look at, before you jump in, ICQ2. So this is how much? 2 milliampere. 2 milliamperes, right? And beta, let's say, is given as 100, 2 milliamperes. What is the value of this current? Assume forward active. What is the value of this current? Base current? 20 microamperes. Okay, fine. This 20 microamperes. What is the value of the collector current here? This is what? Emitter current, right? Emitter current. Now note, all of you know that IC is beta IB, IE is beta IB, which is IC plus IB, so it's equal to beta plus 1 IB. And first order approximation, there is nothing but equal to IC. IE is in forward active, in forward active. Okay, in forward active, IE is equal to IC. So this is also 20 microamperes. What is the current flowing in 2K? Almost what? Almost 2 milliamperes, right? Because the current flowing would be 2 milliamperes plus 20 microamperes. So 2.02, which is approximately 2. All right. So what is the value of this voltage? So this is 2. A drop here is 4, and the value of this voltage is 1 volt. So you agree that this transistor is in active mode? I mean, the Q2 is in Q2 is in forward active, agreed? Q2 in forward active. Okay, if this is 1 volt, how much is the voltage from here to here? From here to here? 0.7, right? 0.7. So how much is the voltage from here to here? VCE2. Can you all calculate? VCE1 equal to what? 1 volt, 0.7, 0.3. So this is also away from saturation. But it's getting close to saturation, right? But it's away from saturation. So we'll assume this also to be, in a good design, what you would do is you would make this 2K a little less. If 2K becomes a little less, then what will happen to this 1 volt? May become 1.5, and then you'll move further away from saturation. Okay? So we'll assume VCE1 is 0.3 volt. We'll assume that this is also in active mode here. So if this is 20 microamperes, what is the current here? Point 20 divided by 100, so 0.2 microamperes. Okay, so that also you know. Now can you all calculate RB? What will be RB? How do we calculate RB? What is the value of this node voltage? We said here is how much? 0.7. So what is the value of this node? From here to here is 0.7. What is the value from here to here? 0.7. So total value would be 1.4 volt. The value of this node. So RB would be what? 5 minus 1.4 divided by IB, which is 0.2 microamperes. That will give you the value of RB that is needed. Right, very high value of RB you would, Now this problem illustrates that, you know, this 0.7 that we are doing, we are assuming Q2 for Q2, we are assuming VBE2 to be 0.7, right? Is it fair to assume VBE1 also 0.7? If I want to be more accurate, the current in Q1 is what? As compared to current in Q2, 100 times less, right? The current in Q1 is 100 times less than the current in Q2. So if you wanted to be more accurate, if you're assuming 0.7 for Q2, what you should assume is 0.7 minus thermal voltage VT multiplied by Ln. It's a factor of 100 less, so you know the diode drop, how it goes. So one should have assumed this to be a little less here, if you want to be more accurate. So sometimes you see people taking that. For example, this value turns out to be 0.12 volt. So instead of 0.7, some people may take it as now 0.58. Or 0.6, a little less than that, because it's carrying so much less current. Q1 is carrying so much less current. So you may see in somebody doing an analysis and assuming 0.7 for Q2, but for Q1 assuming to be 0.6. Why? Because the current is 100 times less, and so they're using a diode voltage which is 0.6 rather than 0.7. Somebody may be doing that. Now obviously this would be more, it will make more sense if this were not 5 volt, but if it were considerably less than 5 volt. In a 5 volt, you're subtracting 5 minus 1.4, or you're subtracting 5 minus 1.3. right? 1.4 versus 1.3 may not result in so much error, but you do see people doing this kind of a more accurate analysis by assuming VB1 is this thing as compared to VB2. Okay, so a large variety of circuits now we can analyze by following this particular approach, assuming it to be forward active and then using the basically two things. VB is 0.7 and IC is equal to beta IB, and on that basis we can then do the analysis here. Now come back to this model here. This model that we just built was here. So we are saying that transistor is like this in forward active, beta IB 1 plus VCE by VA, emitter, collector and base. Okay, now I want to build a small signal model. A small signal model. This is BJT, right? BJT. Small signal model. This is IB. This is IC. Now remember, small signal model is what? Incremental model. Incremental model. Model where voltage across the device may be small. Across the device may be small to obtain linearity. Remember, we wanted to obtain linearity, to obtain linear relationship. Right? Remember this about small signal model. So how do we obtain a small signal model? Remember small signal equivalent circuit. Every element is replaced by is incremental model or a small signal model. So this, if I look at, let me draw a model here. So again, now I'm drawing a small signal model. This is emitter, base, emitter and collector, right? And we have to put something in between. So between base and emitter, what do you see? A diode. Small signal model of a diode is resistor, right? Agreed? It's a resistor. It's a resistor. What is the value of the resistor? R would be, let's call this R pi. R pi would be, how do we calculate that? Remember what was the small signal resistance of a diode? RD was equal to? Okay, so R pi would be, if you assume N equal to 1, so it would be Vt by the current flowing through the diode, which is Vt by IB. DC current, this is DC current flow. Or another way of writing this is, IB is IC by, so you can write beta Vt by IC. Right, so this is clear that between base and emitter I should replace by R pi, a resistance, because the small signal model of a diode is a resistance. The issue now is, what do I put between here and here? Okay, so let's examine this thing in more detail. Let's examine this in more detail here. Okay, let's examine this factor here. This factor, which is beta IB into 1 plus VCE by VA. This is nothing but IC. Remember, this is IC. And we have to build an incremental model for all the elements, right? We have to build an incremental model of this. Now remember, when we built an incremental model of a diode, what is the condition for this to be valid? The voltage across the small signal voltage across the diode should be much less than Vt. So now note that small signal voltage, this is valid, the small signal voltage VBE should be much less than Vt. That's the condition that we must obey. Then only I can replace it by R pi. And we call this voltage, let's call this voltage VBE, whatever. You can call it V pi, whatever, anything you can call it, right? So this much is clear, that between base and emitter I have a resistance R pi. And we know how to calculate R pi, how to calculate this. Now let's go back and look at what do we do to this element, IC. Now remember, how do we find, if I give you any element, how do we find the small signal, this thing for it? You know, remember we said if I have I equal to K V square, something like that, we said the way to find small signal model is del I by del V, because it represents a change in I versus change in V. So this gives us 2K V, and then we write this as delta I equal to 2kV times delta V, right? And then we say I equal to, small signal model is I equal to, remember, just to remind you, I equal to V, this we write as V divided by an R, and R becomes equal to 1 over 2kV. V is the bias, whatever voltage it is, bias it, right? We did like this, del I by del V. Okay, now same thing that I'm going to do here, but I'm going to do IC equal to, so now I'm going to write this as delta IC. Can I write now? Delta IC is del IC by del. Do you agree with this statement? Delta IC is del IC by del IB multiplied by delta IB plus del IC by del VCE multiplied by delta VCE. You agree? The net change in IC, can come about because of what? Change in IB or change in VC. Agreed? It's a simple differential form. Delta IC is delta IC by IB multiplied by delta IB, delta IC by delta VC multiplied by delta VC. Okay. Now this change delta IC, what do we write? What do we write it as? Small IC. This, for a moment, keep it as it is. IC is equal to delta IC by delta IB. This we write it as IB, small IB. And this we next write is delta IC by delta VCE. We keep it as it is. And this we write as VCE. Right? Do you agree? Okay. All right. If this is okay, let me remove these things here. Okay. Let's look at this relationship. Delta IC by delta IB. What do you think is from here? What do I get? Take a derivative. Delta IC by delta IB is beta into 1 plus VC by VA. Agreed? Correct? If I take del IC by del IB is beta. Now what are we saying about VC by VA? VA could be 100 volts, VC could be 2 volt. So this factor we are saying is fairly close to 1. So what we are going to do is we'll approximate this as beta. simply beta. We'll neglect this because we are building a simple model, right? We saw the usefulness of a simple model. We are building a simple model here. Okay, so that we'll keep as beta, right? No problem. Okay, next is we do del IC by del VCE. What do we get? Beta IB by VA. Okay, right? Okay, this we can write it as beta IB 1 plus VCE by VA divided by VA into 1 over 1 plus VCE by VA. No problem. Multiplying and dividing by the same factor. So this factor we can write it as IC by VA multiplied by 1 plus VCE by VA. And what approximation I'm going to make? Neglect this and say this is equal to IC by VA. All right, IC by VA. Now this is what we are going to define as 1 over R0, a new parameter. What is R0? R0, a new parameter we define R0 equal to VA, early voltage, divided by the DC current flowing. All right, so this relationship that you see here, this I can now write IC is equal to beta IB plus VCE by R0. IC is beta IB plus VCE by R0. Okay. Right? Okay. So let's go back. So now note that this is IC. And what did we find expression for IC is equal to beta small signal IB plus VCE by R0. How do I represent the first term? Are you saying the first term IC is made up of two terms, right? So the first term, are you seeing that I can represent it like this? Beta IB. Agreed? The second term, I can represent it like this, R0. Note that beta IB is the first term, VC by R0, this is the second term. Correct? Did I make any assumption, big assumption? Was there any non-linearity in deriving this? Is there any relationship? You know, if you go back, I use this, right? Note that these are all linear relationships. This is linear, this is also linear. I didn't have to make any assumptions taking a non-linear expression and saying it's linear over a small range. So there is no constraint on how large VCE can be. How large VCE can be. There's nothing that VCE has to be very small. There's nothing like that. The only constraint I have in my this thing is this VBE has to be much, much less than beta. So what we have done is, note that we have obtained a small signal model. We have obtained a small signal model, which is this model here. So again, base. Note in small signal model, we all use small letters here. R pi, small here. We'll use here emitter small, here beta IB, all denoting small values here. And we use R naught. I see here. This is for a transistor biased in forward active mode, IB. But suppose I write this as V pi. Now, do you see from here that IB is V pi by R pi? Correct? IB is V pi by R pi. Okay? This current source that you see here is beta IB, so it's equal to beta by R pi multiplied by V pi. Okay? Beta IB is beta by R pi into V pi. So therefore, what we can write this current source that you see here, we can also write it as GM V pi. And note, we are talking about a current depending on voltage, so we call it the transconductance. We call it transconductance. What are we writing transconductance? GM equal to beta by R pi. But remember what was R pi? R pi we had said is equal to VT over IB. VT over IB, so we can write this as beta by VT multiplied by IB, and so we can write this as IC by VT, GM. Right, so GM, all these are useful terms here. So I can also write a small signal model of a diode or a BJT like this. Emitter R pi IB and again a current source, but we don't write it in terms, we write it in terms of GM V pi, where V pi we write it like this, and we put here R0. Right? So note how my small signal model looks like. And it also goes by the name hybrid. There's a reason, we'll go into it later on, hybrid pi model here. Hybrid pi small signal model. Note that both are okay. This is also okay and this is okay. This is the model that we'll use more often by putting R pi here, GMV pi here, and R naught here. Okay. All right. So let's say, if that's the case, here is a transistor. Let me draw a transistor. The transistor is biased at a current of 1 milliamperes. it is in forward active mode, is beta is 100. Draw the hybrid pi model. Of this transistor. Draw the complete hybrid pi model of this transistor. What else do you require? I've given you beta. Is there something else which is required? Note that you would require also early voltage, say 100 volt. So I have to give you beta and I have to give you 100 volts. What is the hybrid pi model of the transistor? And I need to also specify that temperature is 300 K, and therefore you can assume thermal voltage as 26 millivolt. This is also something that we commonly assume. So basically what we need to do is get into the habit of drawing the model. You need to put R pi, and you need to put, there are 3 elements. You need to put GMV pi, and you need to calculate R0. 3 elements. Right? Draw the element, base, emitter, collector, and the 3 quantities you need to find out: R pi, GM, and R naught. Alright, so it's a clear R pi. It would be GM, we can calculate quickly, IC by VT. Alright, will turn out to be, IC is 1 milliamperes, this is 26 millivolt, I think 0.038 ohms inverse. R0 is straightforward to calculate, 100K, basically VA by ICQ, VA by IC. Note that this DC current I must know. I cannot calculate a small signal unless I know this. So this is 100K. And R pi is, one way of calculating is beta by GM. So, 2.6K. So note that typical values you already know. 2.6K, GM is 0.038, R naught is 100K. Right? These are some typical numbers to keep in mind. If my bipolar transistor is biased at 1 milliampere current, then R pi is 2.6K, GM is 0.038, R naught is 100K. Okay. Right. All right. So let's continue then. So here is our transistor. Let's make this model a little bit more accurate. So let me draw a transistor here. We draw a transistor like this, simple. We say N plus, we say P, and we say here, and here, and here. Emitter here, base here, and collector here, right? And the model that we have drawn, small signal model, is R pi, GMV pi R naught. Okay. Now we are talking about forward active. Which junction is forward biased? Base emitter junction is forward biased, right? Base emitter junction or base emitter diode is forward bias. Collector base junction is reverse bias, right? This is collector base junction. In a reverse bias diode, right? Did we say that as the frequency goes up, the reverse bias diode has a capacitance? Diode has capacitances in it. Reverse bias diode has which capacitance? Depletion capacitance only. Remember, there's a diode. If I have a diode here, a PNN junction, there's a depletion region that we discussed. And in reverse bias, there's nothing but a diode which we call it a CJ, right? And we say CJ equal to CJ0 and all that expression. Okay. Now, don't you think that between base and collector, I should put a capacitor here? Between base and collector? Between base and collector. Look at this junction here. It's a reverse bias junction. So I put a capacitor here, which will be of this form, CJ. Except that we have a specific name for it. We call it C mu. C mu is what? Collector base junction capacitance. Correct? C mu is collector base junction capacitance. It also has a similar kind of an expression that we have seen. So if we want to complete our model, we have to add capacitances also to it. Okay. Now let's look at the base emitter junction. Base emitter junction is also forward biased. It also has capacitances. How many capacitances does it have? Forward bias junction? Junction plus diffusion, right? Both these capacitance. So base emitter junction will have a junction, we can call it junction capacitance, CBE, CJ maybe E, plus a diffusion capacitance, C diffusion, right? Two capacitances are going to be there. Base emitter junction. We're going to combine them and we can call this a one single capacitor, which is called C pi. Note that this capacitance is the diode capacitance, C pi. But it's a forward bias capacitance. It's a forward bias capacitance. So we get this C pi and we get this C mu. And C pi has two terms in it. C pi has two terms in it because it's forward bias junction. So it has a junction capacitance and it has a diffusion capacitance. Right? So now this is becoming a high frequency model. High frequency model of small signal, high frequency model of a BJT. Small signal, high frequency model of a BJT, because we've added capacitances to it also. Right? We have added capacitances to it also. So let me redraw this model here. So let's redraw the model. So we are going to do a R pi emitter. We are going to add a capacitor C pi. We're going to add a current source here. voltage dependent current source, GM, V pi. We're going to add a resistor here, R0, and we're going to add a capacitor here, C mu. This becomes the collector, this becomes the emitter, and this becomes the base terminal here, right? We know how to calculate R pi, we know how to calculate GM, we know how to calculate R0, right? Now we need to know how to calculate C mu and C pi. So C mu will be given by an expression like this, CJC0, because it's collector junction capacitance, 1 minus collector base voltage divided by some VBI to the power M. So if some these values M, VBI, CJC0 is given, and collector base voltage you know, you will be able to calculate C mu. C pi, on the other hand, will have a junction capacitance, CJE0. People may use slightly different terms, CJB, CBE and all that. 1 minus VBE versus VBI to the power. If you want, you can call it MC for collector junction, ME for collector. So that's the junction capacitance. And then there is the diffusion capacitance. Do you recall diffusion capacitance? What was it? ID. Remember, for a diode, it was the diffusion capacitance was ID by Vt into tau, right? Now in this case, it is IC by Vt into tau. And this IC by Vt, all of you know, is nothing but GM. And we call it tau F, forward, because we are talking about forward active mode here. So we write it tau F. So that's how we calculate C pi. If we know CJE0, we know built-in voltage, we know this coefficient, grading coefficient, and GM anyway we know, and if we are given tau F, we'll be able to calculate what is C pi. So we know now how to calculate all these things here. R pi, GM, R naught. We need to be given these values. We'll calculate C mu. We'll be given these values, all these values. We'll be able to calculate C pi. Right? All these values we'll be able to calculate. There's one more term which is we would like to add to this particular model. One more term, and then the small signal model would be a reasonably accurate model. And let me explain where that one more term is coming. Note that I've been drawing this transistor like this. N plus P and N, and I'm drawing like this. Emitter, base, and collector. The transistor is not like this, right? It's not a bar like this. The way the transistor, actually a better picture of a transistor is like this. You know, let's say this, I'm drawing a cross section. Transistor could be a piece of N-type silicon. Or let's start with P-type and actually make it bigger. All right, say P-type silicon. Now you know how the transistor would be made on, this is a P-type silicon. What they would do in this region here is that first they would take a place and they would make a region which is N-type here. They are making collector. So it's already P, and they will diffuse impurities, right? To make N-type, you have to diffuse or implant this N-type impurity, like arsenic. So they will make this as N-type. This is N-type. Then within this region, they will make this region a P-type. Then within this region, they will make this region N plus N-type here. Right? So do you see where the emitter is? The emitter is here. Emitter at the top. Where is the base? The base is here. Base. And where is the collector? Let's say the collector could be here. This is Npn. So when we draw this transistor, no, what we are drawing is we are taking a line like this and we are drawing something in between, N plus P and N. That's what N plus P and N. But the transistor actually looks more like this. Transistor looks more like this. Okay, this is the now you may be wondering, why do I make P? Now this is one transistor. Let's say transistor number this is Q1. So let me make another transistor here. Another transistor. N plus P and N. This is another transistor. If we call it emitter 1, collector 1, base 1. This is emitter 2. This is base 2. And this is collector 2. Made on the same substrate. See, all the transistors are made all simultaneously. When I'm making this transistor, if I call this transistor Q1, let's call this transistor Q1. Then I call this transistor Q2. And I could make Q3, Q4, you know, when I'm making this end, I'm making this end all simultaneously. So I can make hundreds of thousands of transistors all simultaneously. I don't need anything extra. It's not that one transistor is made and then the second transistor is made and the third. All transistors are made all simultaneously. It takes the same effort to make one transistor or 100 transistors. While you're diffusing impurity, you diffuse it everywhere, wherever you want. So you get this transistor Q1 and Q2. Now you realize this is what I'm calling as the substrate terminal. This one. This is the substrate. Right? This is a substrate, silicon substrate on which I'm making. So I have this base, emitter and collector. I have base, emitter and collector. Why did I choose this p-type? Why this p-type? Now note that this transistor has to be isolated from this transistor. Q1 and Q2 are two separate transistors. They need to be isolated. Right? So what I do is, to the base, this substrate, we apply a large, not large, but we apply a sufficiently large negative voltage. What does it do? When you apply a sufficiently large negative voltage, if you note that this is P, right? Between this N and P, what do you see? There is a diode, right? Between N and P, there is a diode. Between here, what do you see? There is a diode here, right? PN junction. But if I apply a large negative voltage, what happens to this PN junction? Reverse bias. Similarly, between this and this also, you see, between these two regions, you see a diode. It's also, if I apply a large negative voltage, this diode is also reverse bias. So this N region and this N region are connected by what? This N region and this N region are connected by two reverse bias diodes. And two reverse bias diodes are like open circuit. So the two transistors Q1 and Q2 are isolated. That's why this P region is there here, to isolate it. Okay, to isolate these two regions here. All right, so that's one thing. Now, so you note that in a bipolar transistor, when you're making it in an IC, there is a fourth terminal. And what is the fourth terminal? The substrate. Substrate is also there in my, when I'm making my transistor on an IC. And the substrate is what is kept at a negative DC voltage. A large negative DC voltage. Its purpose is to reverse bias both those diodes. Now a DC voltage in small signal, what does it appear like? In small signal, what happens to a DC voltage? It's like ground, small signal ground. But do you see that this collector, this N-type is a collector? Between collector and substrate, what do I see? Between collector, this whole region is collector, okay? P-type, N-type, and this is P-type. Between the collector and substrate, what do you see? A PN junction and a reverse bias PN junction. Do you see that? Between collector and substrate, there is a PN junction. It's a reverse bias PN junction. Under small signal condition, what does a reverse bias PN junction do? What does it appear like? Reverse bias PN junction is what? A capacitor. So what I should do is, if I want to make this model more accurate, right? What I should do is the following. This is my collector, fine. Between collector and this substrate, but substrate will become, this is actually substrate contact, remember? Substrate, but it becomes a ground. I should add a capacitor here, which is called the substrate capacitance. You see that there's another capacitance that is there between collector and ground. So this capacitor may also be there in some of these devices, circuits that you're making, between the collector and the substrate. And the substrate is, because it's DC, so we put it to ground. There's a there's the substrate capacitance here. So there's an additional capacitance that is there from the collector to the ground, small signal ground here. All right, that's one thing. The other one is, note that base terminal is here, right? Base terminal is here. Where is the transistor when I'm saying current is flowing? The current is flowing like this, right? Current is flowing like this here. So actually, when you apply a base current, if you look at base current, when I say IB, so base current starts from here and there is a resistance here. It has to, before it reaches this point here. Right? Do you see that there's a resistance through this and then it reaches, and then of course the current starts flowing. So if I want to be more accurate, normally what I need to do is put a resistor here. That resistor that you see there, starting from the contact and eventually reaching the place where the transistor is actually there. This is where the transistor is, right? This is where the transistor is there, NPN. So, but contact is here at the top. So in order to reach the place here, there is a resistance here. And we call that resistance a base resistance, and it goes by the name RBB. And additional resistance that we need to put. So many times, especially when you do high frequency analysis of the bipolar circuits, you have to know RBB. RBB is very important for high frequency analysis. High frequency analysis, RBB plays a very, very important role. So you have to know RBB here, and you have to include CS also. And then the rest I've already talked about: C pi, R pi, C mu, GM, and R naught. All these things are there. In many of these simplified analysis, what we do is, you will see that CS is being ignored. We don't talk about CS, we just ignore it. In many of the simple analysis, we forget about CS. Okay? But in many of the IC amplifiers, you need to take into account the substrate capacitance also. All right, so let's stop here, and then we'll continue with a little bit of BJT circuits, and then we'll go on to MOS circuits here. Okay.